That exact question. And this is my problem how? I don't take it personally, no. Amanda. Who should be monitored with capnography? If these are present in your patient, you should be monitoring with capnography. The European Society of Critical Care Medicine made a recommendation that any patient who's being mechanically ventilated in the ICU should be monitored with end-tidal CO2. We rarely, if ever, use it. Every single patient who is in the OR undergoing general anesthesia is monitored with end-tidal CO2. Any patient who is receiving conscious sedation should be monitored with end-tidal CO2. And I know that's not done either. But if your patient has ventilation, which I'm hoping they do, otherwise we have to talk. If your patient is being perfused, or if they have metabolic activity, we should be monitoring their end-tidal CO2 level, because all three of them play into the process. We normally just think of the one on the right, but in reality, CO2 is very perfusion dependent, and actually it's very dependent upon metabolic processes also. If you are hypometabolic, is that a word I want to use? If your metabolic rate is reduced, your end-tidal CO2 is going to be reduced also. Tell you a little, let me pause it here. Tell you a little story, my little rant. All three are important is the bottom line. Okay? They all play into the creation of CO2 being exhaled. Multiple ways to attempt this. Mass spec was kind of the cool thing back in the early 80s. Mass spectroscopy was basically where we would ionize with radiation the gas as it was being exhaled, and the different molecular weights of each of the gases would fall out at different spots onto a collecting plate. Talk about a cool technology, but just totally not practical in the ICU. But it was one way that you could do it. So this basically had this ion beam directing across the gases, and it basically CO2 would fall out differently than other constituent gases that are there. Most of the stuff we're going to use are either mainstream, side stream, or a derivation of side stream that one manufacturer has called microstream. And it actually does have pretty fast response rate, so I'll give them kudos on that one. First of all, let's talk about the mainstream. Mainstream has the sampling chamber, the infrared source, right at the airway detective, right at the airway. Where's my pen? Oh, it's not plugged in. That would probably help. So here is my infrared light, and it's shining across to a photo detector. And as the presence of CO2 is detected, you have the ability then to go ahead and quantify how much you have. Conversely, item B here is a side stream where it's taking the CO2, sampling it, and taking it back. Well, we'll see if this shows up. It's fine. Ignore it. Okay. Some of the important things are these units need to be calibrated. They're typically calibrated with a 0, often just exposed to room air, since the percentage of carbon dioxide in room air is 0.03%. You're looking at a very nominal value there. It's also calibrated typically to, I think it's a 4% or a 6% CO2 gas to get a value that's higher on the higher end. Very important to control for moisture. Any collection of humidity on the photo detector impairs the ability to be able to analyze correctly. This is definitely true in the mainstream because the mainstream gas is passing right along, has humidified gas passing right in front of the sensor. But it's also true of side stream analyzers because as that humidity is pulled back, the ambient temperature drops from what's in the airway, and you have condensation being created. Depends upon how fast the sample flow rate. It's one of the beauties of the microstream is that although it's a side stream analyzer, its sampling rate is almost as good as a mainstream. So you don't have any lag that is there. How long the sampling time is, the transit time, what the response time is. These are all technical problems that can be involved here. Here's an example of a side stream and a mainstream. So this is, let's see, I got this correctly here. This is side stream. This is mainstream. So main here, side here. And this is where the breath actually starts. This is looking at actual breath origination. And what you notice is that as the breath starts, you end up seeing end-tidal CO2 starting also. Or in this case, as exhalation starts, you start seeing the expired CO2 coming. And as the breath then triggers itself back into inspiration, you see a zeroing of it. So mainstream is in sync with what the ventilator is doing. Side stream is always going to have a bit of a lag. So in other words, here's the start of exhalation. The start of exhalation on my capnogram doesn't start till much later. Why? Because it's got to be sampled back, and there's always going to be a little bit of a delay in there. So as far as looking at a capnograph, you should be able to tie what's going on in ventilator phase to what's going on in end-tidal CO2 phase. Mainstream is pretty close, almost exact. Side stream's always got a little bit of a delay. Does everybody see that? Okay. Just going back to the normal time-based capnogram, where we're having time on the x-axis and end-tidal CO2, or I'm sorry, and exhaled CO2 on the y-axis. Giving it in a couple different values here. We typically only look at this one, millimeters of mercury. Sometimes you'll see as a percentage. The old Easy Cap, if you look at it, the color changes. They had it marked off in percentages of CO2. And if you're really a nasty person, you flip it over so that it's now measuring in kilopascals, and everybody gets screwed up. It's totally that's what they do in Europe, not around here. But there's four basic phases that are present. Phase 1 is the inspiratory phase, and hopefully you're not seeing any CO2 being created. So this should be at the 0 point. If it's anything above the 0 point, that means you've got some rebreathing of CO2 present, and that should never happen on a mechanically ventilated patient. Phase 2 then is where we start having a mixture of alveolar gas and dead space gas, because as that gas is coming out, the first part of the exhalation is going to end up being very low in CO2, because it's basically within your anatomic dead space. Then as that CO2 continues to be exhaled, you're going to see a rise back up again. So initially it's going to be very low, and then as it rises, it probably is not as square as this is depicted. It's more along this line, so that you don't reach the total CO2 until what will end up being a plateau and eventually an end-tidal value until the very end. Phase 3 is the plateau, where it's looking strictly at alveolar gas, and you're going to see basically the continuation of CO2 until the very end of that breath. And then phase 4 is the start of the next inspiratory phase where we're washing all the CO2 out back to a level of 0 in the process. Some abnormal waveforms. These might make good test questions, just saying. Sudden loss of end tidal CO2 to 0 or near 0. This is basically where you're not having any CO2 being sensed, and that is indicative of either a total disconnect, esophageal intubation, tube has come out, obstructed endotracheal tube, not a good thing. This is a situation where we need to immediately identify what the source of the problem is. It's where it goes immediately to 0 or near 0. Contrasting that with an end tidal value that is decreasing as time is going on. So it may be an end tidal value of 35 here, 25 here, 20 here, and it's gradually going down as each breath subsequently goes. This is usually associated with perfusion problems, specifically a situation where perfusion is decreasing. Loss of blood pressure, cardiac arrest, and they're still hooked up to the ventilator. So I'm still sampling the CO2, the ventilator's still washing it out, but as that perfusion keeps going down, and there's no CO2 coming back, it eventually washes itself out. But it's a much slower process. Saddle embolism would be an example. But it's all related to perfusion. Okay? As I have a reduction in perfusion, you see this decrease in PCO2. It's exponential in nature, but it's not sudden. It's not automatically going to 0. Here's an example also of one where it's a decrease, but it's on a much, much slower basis. So instead of being that, what did I have it start off, 35? Yeah. This would be, it's at 35, 34, and it's just going down on a much, much slower basis. And this is basically something where, again, it could be perfusion being reduced. It could also be just that the CO2 production is reduced. So we'll see this in the OR when they start cooling them down. You start having metabolic rates slowing. You're going to have less CO2 being created, less CO2 being exhaled. Some other little weirdnesses that are there. There's something called the curare cleft, where you're seeing little triggers happening in the midst of the breath. And this is basically an example of patient's efforts, specifically somebody who was previously paralyzed but is now coming up out of the paralytic. Curare, if you don't know, is a predecessor to a lot of the non-depolarizing paralytic agents. It was what they used to use on the tips of their darts to poison people in the process. Cardiac oscillations can also cause a little bit of an artifact just because you're having, especially with a higher blood pressure, you're having that pulsation being sent. It can actually be picked up on the end tidal CO2 waveform, and you can see how it's kind of like in sync with the EKG in the process. I don't know if I blew this up for you in the back. I think I did. If not, this is something that's out of Malley, chapter 15. You know, that red book. But it basically is talking about different reasons why you might have an increase or a decrease in end tidal CO2. Did I not?
No.
Okay. Well, there it is. It's in Malley. So, might make a good test question when we come around to it. And a lot of it is just stuff that you should know. If you have an increase in CO2 production, you're going to have an increase in end tidal CO2. Reduction in alveolar ventilation, you're going to have a rise in end-tidal CO2. And you can see there's some differences there between whether or not equipment malfunction will go one way or the other. So where do we use it? We can use it in weaning. Instead of having to do repetitive arterial blood gases, and Glenn was mentioning that, they just want to use end-tidal CO2 to be able to get an idea of it. End-tidal CO2 pulse oximetry, who the hell needs a blood gas analyzer? Well. If we're in a situation where we want to hyperventilate somebody, say for a head trauma, it's nice to monitor with end-tidal CO2 there also. It's also nice to monitor ICP on those patients, and ideally having a implanted oxygen sensor to be able to identify a cerebral PO2. And in cardiac arrest, we know about the EasyCap being utilized. I think we finally got people to use some mechanism to verify endotracheal intubation versus esophageal intubation. But now, again, we're looking at external chest compressions where normal end-tidal CO2, this is what AHA says, 35 to 40 millimeters of mercury. I think we learned a little bit different value than that, but okay, whatever. Again, this is AHA. And their recommendations is whenever you have a value that's falling below 10 millimeters of mercury, you should get a new rescuer onto chest because they're not doing effective compressions. If you don't do effective compressions, you're not circulating the blood, blah, blah, blah. And then lastly, there's the restoration of spontaneous circulation that they have, where you're at, 15, 16, 37. All of a sudden now you have a restoration of a spontaneous pulse, and it's a way to evaluate, do we still need to continue CPR at that point in time? So I'm at a level between 10 and 20 typically, and all of a sudden it spikes up. And that's all that CO2 that was peripherally trapped because of poor cardiac output now being picked up and brought back. And it's an indication to evaluate the patient for that, what they call ROSC, R-O-S-C, restoration of spontaneous circulation. Whatever. Okay? So ideally you should see that being done. I know it's not. And I think I'm going to stop right there because I'll pick up on volume capnography later. But